Well, good afternoon. I'm glad to open our new season, a new semester of Research Exchange presentations. I'm Kostas Panos. I'm the director of CITRIS. And I would like to welcome you and also the viewers on the web from the other campuses. So a few announcements before we start today. This semester we have a new seminar series in conjunction with the Institute of Transportation Studies and the Trust Center focused on resilience. This is going to begin in March, and all the information about this is going to be online. We have a bunch of events happening all the time, and this week actually we have two of them happening. One of them is Women Entrepreneurship. It's happening tomorrow, Thursday, between 6 and 8 p.m. in this auditorium. And this is going to be a very exciting event because it's going to bring together alumni and current student women entrepreneurs. So it's going to be very interesting to come and watch. We have another event, another entrepreneurship event on Friday. This is going to be the Berkeley Entrepreneurship Expo. It's going to be Friday between 12 and 4 p.m. and it's going to be happening at the atrium right outside this auditorium. So let me now go to the main event. Today we are happy to introduce the first speaker for the semester, Reza Abbaschian. He began his tenure as Dean at the Bourns College of Engineering and Distinguished Professor and William R. Johnson Jr. Professor in September 2005 at UC Riverside. Prior to his appointment at UC Riverside, Dr. Abbaschian was at the University of Florida, where he also served the chair of the department for 16 years. He has received his PhD in Material Science and Engineering from UC Berkeley, so he's one of us. So glad to welcome you back. He has published more than 250 papers on subjects ranging from metal processing to composites, solidification, and high temperature, high pressure growth of jewelry diamonds, and that led to the formation of a company called Genesis Diamond Company. The emphasis of Dr. Abbaschian's research is the fundamental understanding of the role of interfaces on the processing and/or properties of materials. His current projects involve investigations in solidification, high pressure, high temperature growth of diamond crystals, and electromagnetic levitation processing of alloys. However, I understand that today Dean Abbaschian is going to tell us about the role of material science in education and how he views that role in his leadership at UC Riverside. Dean Abbaschian.
Thank you. Thank you, everybody. I'm delighted to be back here. Last time I was here, I'm not going to say when it was. I was sitting on the other side, and I'm delighted to be back here and standing in front of you. Obviously, Berkeley has a special place in my heart. You know, I was here when many of you were not even born, and this is where I met my wife, who was going to Mills College in Oakland, okay, and we have been married since those days, okay. But I decided to give the talk about material science and engineering because that's the field that I got educated here, and after graduating from here, I had numerous appointments, and before joining UCR, I was chair of Material Science and Engineering Department at University of Florida, okay. And then I decided to go after dean position. But we started the Material Science and Engineering program at UC Riverside, and I wanted to share that with you today. And please ask questions anytime you have. I don't know if the audience from other places, how they ask questions, but from the audience here, just stop and raise your hand, and I'll, hopefully I'll be able to answer them. I decided to keep my talk a little bit general in nature. I didn't want to go into details of phase transformations, kinetics, solidification, and so on. Although I could give a lecture on making diamonds, and which is, one of the most exciting materials that's metastable. It shouldn't be as it is, but it is. Okay. But today I'm going to talk about material science and engineering. Just to set the stage, first I'm going to introduce University of California, Riverside, your sister campus, and also Bourns College of Engineering. Then I'll give a little historical background about materials education, then talk about UCR approach and why we believe this is it, kind of what the future material science and engineering is going to look like, and then finish up with a graduate program if we have time. I can talk about research activities, but we will stay today mostly on the educational side. Okay, about UCR, okay, you can see a view of the campus. Okay. We are one of the 10 UC campuses. In fact, when you look at UC system, of 10 campuses, 3 of them are inland. We are one of them. Merced is the other, and Davis. Okay. All the rest of them are in the kind of near the coast, and because of that, they have expensive real estate. For us and Merced and Davis, that doesn't seem to be a problem. The Riverside is about 60 miles east of Los Angeles. In fact, if you drive from Los Angeles to Palm Springs, you drive through Riverside. Okay. The campus itself now has around 22,000, 21,500 students, much smaller than Berkeley. Our undergrads about 18,000, graduates about 2,800. Okay. Now, of course, you know, my alma mater, Berkeley, is always ranked among the top, and in engineering among the very best and so on. But UCR also is ranked highly in some aspects. Like in 2014, Time magazine ranked us number 1, and Washington Monthly has ranked us number 2. The reason those kind of designations is that we have very diverse student body, and we take pride in what we do in order to help these students achieve their goals and aspirations. Okay. And we are the only public university in Inland Empire, which is a huge part of the state. Our economic contributions to the state is $1.4 billion, not as high as Berkeley, but again, it is substantial. That's in fact very important that we let the politicians know that these universities contribute to the economic development of the state. We have huge property. I see that you are running out of space. Back when I was here, we didn't have all these other buildings, but in Riverside we don't have that problem yet, but we will. Our campus started in 1907 as a CITRIS experiment station. Then in 1954, we had College of Arts and Letters formed. In 59, we became basically a general UC research-focused campus. Okay. Of course, among the most milestones in 1989, College of Engineering was formed. Okay. So again, we are a fairly young college, only 25 years old. Okay. But one thing I have put here is that really the applications, the demand to enter our college and university is increasing tremendously. In fact, this coming year we are going to be accepting about less than 10% of students who want to get to engineering, and they are UC eligible students. Okay. Let's talk about our college. As I mentioned, we are only 25 years old. So our first graduates have not even retired. Okay. But in spite of that young age, we are highly ranked. U.S. News and World Report, which is not rocket science, they rank us 69th among top third among all those College of Engineering that are ranked. Among public universities, we are 39th. In fact, if you think of that, it is a tremendous achievement because every state has kind of flagship campus. And, you know, states like California have several top College of Engineering. So we are very proud to be in that. Leiden ranking, which looks at impact of faculty activities, contributions, collaborations, and success of students, ranked us 10th internationally among some 478 that they ranked. And National Research Council has ranked us on top quartile. So we are very proud of this, even though that we are young. And the reason we have achieved such recognition is because of the students like yourselves. Okay? When they come, they graduate, they go and compete with the best in the world and succeed and bring us recognition and name. We are fairly small college, 96 faculty. Okay. Undergraduate enrollment 2,300, graduate 660, and about 500 of them are PhD, 170 masters. In fact, when you look at this ratio, other UC campuses, master's students much larger than compared to the PhD than us. For our case, since again we are kind of in rural areas, most of our students are PhD focused, where for example if you are in Bay Area or you are in Silicon Valley, you have a lot of practicing engineers that participate in your master's program. We do about 37 million on research expenditure, endowment, and we have 10 endowed professorships. This is the thing which I'm most proud of. 81 of our faculty are members of professional societies, fellows of professional societies, not members, okay? And diversity is, as I mentioned, an important part. 34% of our students in our college are underrepresented minority. Okay? And because of that, ABAT 2009 recognized our college with a Claire Filbinger Award for helping these students and succeed. Okay? Now let's go into departmental structures. We have 5 departments: biochemical, computer, ECE, mechanical. We have material science engineering. That is not a department, it is a college-wide program. And I'm going to be spending most of my talk talking about this program. Why didn't we create department? Why did we come up with this model? We get degrees on traditional areas. All are ABET accredited except business informatics, which we give jointly with the School of Business. Okay. That one, the accreditation is not clear who should accredit it, business side or engineering. PhD and masters, the same areas. We also have started online master's program that is being unveiled right now, and next year we are going to accept students in that arena. Okay? And we also have several research centers that I will not go through them, but basically bioengineering research, environmental CCERT is well known throughout the world in environmental research and technology research. If some of you may remember that Riverside used to be famous for air pollution. And about 22 years ago, we started this center. The goal was to find out where this air pollution is coming from and what to do about it. Okay. So they did a lot of studies that have been used in writing codes and the others. And they, in fact, most important thing, they identified the source of the pollution. And lo and behold, it wasn't being generated in Riverside. It was in Long Beach or Los Angeles, so things had to be solved there, which is a good example of global impact of environmental issues. You couldn't have solved the problem of pollution in Riverside alone unless you put a huge wall. Okay. But you had to go out there. So we are very proud of those activities. We have Center for Nanoscale Science and Engineering clean rooms, similar to the ones you have. CITRIS, which is on intelligent and audio and video visualization. UC Light, which is basically wireless optical communication using LEDs, and I believe UC Berkeley is partner in that center. SC Rise, which focuses on solar energy, Winston Chang Global Energy, which is the second youngest center we have created. Here we have an integrated system of solar energy generation, storage, distribution throughout the city. We partner with not only with the companies, also City of Riverside and public utilities. Because again, one of the reasons we established this is because if you look at solar energy or wind energy production, it is intermittent. How are you going to store it? How are you going to distribute it? To go in and out of the grid is a major issue that is not solved nationwide. Okay, we are making small panels here and there in buildings and houses, but in a massive way we have not solved the problems. And we created that, and it has about 1.1 megawatt storage capacity as a demonstration to show that one indeed can do these kind of research in a massive scale. Okay? And of course, POEM is our way of getting into humanities area, so we created that center, we call it POEM. But anyhow, focuses on phonon-optimized engineering materials. Okay? Now, let's get into material science and engineering. I'm going to give some historical perspectives. Okay? Many of you know that material science and engineering used to be in old days mining, metallurgy, or ceramics engineering. Okay? But came about because of the demand on materials research, demand on having a different type of education. Okay? Initially, when these changes were done, say a metallurgy department became material science engineering or materials engineering, or a variety of names, there was confusion. What does the field or discipline consist of? When you say civil engineering, it is very, well-established discipline. You can define it. Mechanical engineering, you can define it. Electrical engineering, you could at least define it those days, even though that now they are also becoming much broader. But in material science engineering, that definition, that acceptance nationally was not there. You could ask professors, what do you do? What do you teach? Why? You could ask students, what are you studying? Everybody would give you different stuff. So at that time, National Research Council had a study going on, which was basically material science engineering for the 1990s. And the theme was, how do we maintain our competitiveness through age of materials? That report came out in 1989. What the report did was come up with a definition for the field and focus on what the core educational aspects are. Okay? And of course, at that time, they had to define materials. Again, this is 30 years ago. They were defining materials, structure materials, electronic, magnetic, photonic, superconducting materials, which was very popular, biomaterials. Okay? Then they also trying to not only define the field by the materials type, also try to define the field by activities. Material synthesis and processing, characterization, analysis, applications, and so on. So these were the kind of things that they used as an input to come up with this unified definition of what material science and engineering is. Material science engineering, they defined, is the field that deals with these four elements of tetrahedron. We can start from synthesis and processing, structure composition, properties, and performance. When you learn all these subjects in a coherent and unified fashion, then you are basically a material science and engineer. That was the goal at that time. Okay? Of course, the reason as they were doing it, and this study was done, which was led by Mert Flemings and Praveen Chaudhuri, was that, as I mentioned, to maintain competitiveness, we had to look at materials. Everything every engineer uses is made of materials. Okay? So if you want to talk about manufacturing, if you want to talk about competitiveness, if you want to talk economic, benefits of anything, you have to have a materials at the forefront of those. So, these were the kind of themes that they were using in those days, one-liner, that we don't make things, we make things possible and make them better. Okay? You can think of it again. This morning you woke up, the first thing you touch is materials, from all the way from toothbrush, all the way, everything that you do. Okay? So we have to have marketplace if you are going to create new materials. That's an important one, because as a material science engineer, we are always making things better and new. If nobody uses them, then that invention, that discovery just stays in the shelves. Okay? And as I mentioned, no engineer can make these. And of course, one thing has also become since then is that MSE is a hub of materials activities in any university. Okay. Doesn't matter if the university is focused on medical or environmental or bio, materials somehow becomes at the middle. Okay. And of course, in those days, they had identified these existing opportunities. The reason I put this together, some of these are still part of the future needs and opportunities. Some of them have disappeared because we have come up with different way of doing them or accomplishing. But productivity improvement has been around. They keep talking about it. But for material scientists, that definition is very different than, say, operational research type activities. Okay. Now, after that study was done, then we looked at how new materials are introduced into the marketplace. Here I'm giving an example of single crystal turbine blade that is now used in jet engines. If you look at history of that, it started around 1980, it got implemented around 2000. But 20 years for a new idea, novel concept, novel processing takes for industries to use that. You can apply this to any other material, from rubber, from composites, things like even semiconductors. Okay. It is taking about 20 years on the average for the new materials to get into the market. The question is why? So because of that, in 1999, about 10 years after the first study was done, another group was put together with the idea that we have to have stronger linkage to the users. Because again, the thinking was that if you want the materials to be implemented, used more, okay, you get together, connect with other engineers. Don't work in isolation. Okay? And I was part of that group that we worked together. And basically, the objective was, as I mentioned, we know that materials is playing a critical role. We know that things are happening, but what is our role in the next technologies that will be coming about? And again, the thing which came up in that one is, how do we now contain materials science and engineering as a discipline, and how do we define it further? What came out of our study at that time was that take the tetrahedron that I talked about, structure, properties, performance, and processing, add another component to it. That has to be part of material science engineering, that is end users. And when you talk about end users, you also have to incorporate constraints. Constraints could come at variety of ways. Strengths of the materials, recyclability, environmental impacts, all these are the kind of constraints that has to be part of material science and engineering education and research. So we kind of expanded the field this way, okay? And then when you want to do these things and connect to other users, other engineers, okay, you have to find out how you can do that. So for example, if the research that you are doing is related to structure and properties, most likely you are going to be connected with physics, electrical engineering, electronics type folks. If it is properties and applications, you will be most likely dealing with civil engineering, mechanical engineering, or synthesis and processing, chemical, dental, and the others, and structure processing, chemistry, medical guards. So this is how at that time we tried to address the connectivity to end users. Okay. Again, we are connecting to a group of engineers. Okay. Then you look at where the students are going. These are the listings that I had from University of Florida. You see that our students are all over. Aerospace, auto, biomedical. When you are training an undergraduate, freshman year, we don't know that where they are going to end up. So if the students are distributed throughout different industries, then our education has to respond to that. This is also reflected in a number of societies that represent material science engineering. Whole bunch of societies from Crystal Growth Association all the way to TMS and MRS and ASM, the others. This was another way of it's showing that material science and engineering is indeed not a discipline but a field, and I'll get into that. With all these, you look at the departments, material science and engineering departments, they are fairly small compared to electrical engineering, compared to mechanical engineering. We are on the average about 15, 16 faculty per department. Obviously, if we need to satisfy all the things that we talked about, we couldn't do with this number of faculty. So that was a challenge that departments immediately realized. So what did they do? Okay, we started combining with other engineering departments. Like if you look at, since that report came out, 20% of the departments that were material science and engineering changed their names. They joined with chemical, mechanical, aerospace, and the others. Since then, this trend has continued. Okay. So that was one approach that we took. But then again, that couldn't answer all the needs of the field. The needs, as I mentioned, was that basically material science and engineering, sitting here, we were required to take every basic science and engineering principles and apply them, provide and answer societal needs. So based on that, really a lot of people, including myself, rather than calling it discipline, we started calling it material science and engineering as a field. So again, to contrast between mechanical or civil engineering, it is very broad, all the way from science to end applications and sociology involved, environmental issues involved, everything else. Then the challenge was, how do we provide education in 4 years in that broad field? How do we integrate? And how do we balance between science and engineering aspects? Because if you go too much in this side, you are going to be providing applied research, applied education. If you start in this side, you are going to do more sciences. Okay, how do we balance these? Okay, so I'm not going to go through this as different demands on the materials and so on, but at the same time, everybody wanted to reduce the number of hours that the students spending at the universities to get bachelor's degree. So the field is broadening, number of credit hours, unit hours are shrinking, and what do? We provide a lot of electives. We come up with a set of core topics. We make sure that we cover these core topics. Then additional application is provided by specializations or electives. So again, this is different way of taking tetrahedron, processing properties, structure, applications, and put on top of that different classes of materials: ceramics, electronic materials, metals, polymers. Again, based on that tetrahedral model, or the ones that we later defined, we have to cover the entire field for all these properties and all these classes of materials. Approaches that we took at those days was either cover the field in this direction or vertically. One we called horizontal integration, the other one vertical integration. Vertical integration is easy to see. For example, a department focuses on ceramics only, but covers the entire field. Okay? And then others, of course, as I mentioned, you needed to have these core courses, you need to give specializations. Okay? So this was kind of matrix coverage. Okay? And now here comes UCR. So all those are the kind of things that we learned. The field was dynamic, it was growing, it was expanding. We had constraints, not only because of the materials properties, because of the manufacturing issues, because of the cost, because of environmental issues, everything. You go on and on and on. But on top of that, we also had constraint on the amount of time that we can spend to give the degree. Okay. So in UCR, rather than having a department, we put an interdisciplinary program. That's the college-wide in undergraduate and campus-wide in graduate. Okay. We have faculty that participate from engineering departments and physics and chemistry. Biology is coming on board, fairly soon. Okay. So that's our approach. Okay. Now, how does that help us? To begin with, students can come to this program through any of our existing departments. You can come to material science engineering directly if you wish. But since if you have an interest in an area, let's say if you have an interest in biomedical application side, you come to the program through, you come to the program through bioengineering. Okay? Or you come through electrical and the others. Okay? But what it does is that it enables all these departments partner with material science engineering or take a share of the ownership of the program, which is very different than taking a materials and say combining it with chemical engineering and call materials and chemical engineering. This is no, they take the ownership, and more importantly, I'll elaborate on it, the faculty that we hire, they are jointly hired between ME and MSE. Half of their teaching is in mechanical, half of their teaching is related to MSE courses. Their research is at this boundary, the same as to all other departments. So we are addressing the needs, we are connecting material science engineering with engineers that we have, and we are hiring faculty members that satisfies the needs of both. Okay? And these are the core faculty. We have added more. Like for example, David Keselis is in chemical engineering and materials. Hunan is bioengineering and materials. Okay. Roxanne is in electrical and materials. So we have hired faculty members like this, and we have succeeded in finding the right faculty in all of these areas. Because note that what has to happen is that these candidates or these faculty members that we are hiring have to satisfy both their own department and MSE. And as you know, in UC system, merit and promotion is done by the departments. These faculties sit in the departments of mechanical engineering. Therefore, they have to come, as far as mechanical engineering concerned, to research and teaching level that ME faculty votes on their positively on their promotion. At the same time, they have to satisfy the material science and engineering faculty. So this is basically, again, going through what I mentioned. Students enter, they can go through any of these departments, take the core courses, then take specialization courses in these departments, and graduate as an, with MSc. This is a typical course curriculum. You can see that, courses are taught by different departments, like mechanical engineering course, that's Introduction to Material Science Engineering, is taught by mechanical engineering to mechanical engineers and as well as to material science and engineers that are coming from every different department. Okay? Or, others you can say, like chemical engineering 100, that's for our thermodynamics. Okay? So we are not just teaching thermodynamics to material science engineering, we are teaching thermodynamics that is appropriate to chemical engineers and also material science engineering. So I think this is the process that we have put together. Again, I'm not going to go through these things, but basically we are covering these bases by introducing these kind of concepts. Okay? The most challenging part, and faculty members in engineering they appreciate, was ABAT accreditation. Because again, we have so many different faculty members, so many different departments, and we have to satisfy all the things that ABAT requires. So our concern was that will we go through the process? And I was very pleased that last year we did, with flying colors. Okay, I'm not supposed to talk about it, but we did. Okay. And in fact, they have encouraged us to provide these kind of presentations so other departments, other schools start thinking of this approach. So with that, we have a building, material science engineering building, but then again, it is very different. In this building, you see faculty members from all over. Okay? And we have facilities. Graduate program, I'm not going to go through this, but it is becoming much broader. We have some 50 faculty members that are involved in the graduate program. So PhDs and so on are giving. You can again come to any department, chemistry, physics, electrical, get a PhD in material science engineering. Okay? You don't have to worry about whether you applied here or applied there. And each department that you come in gives you a little bit more flavor of that department, and more importantly, that we had not counted on how important it is, it gives you connectivity with other engineers. So you have a network when you are coming through, say, mechanical engineering. Not only you know your network, your own cohort, your own classmates, you are also connected with other mechanical engineers, especially in research projects, senior projects. Typically, they have about 4 or 5 different engineers in addition to, say, business or economic majors as part of the project. So with that, and graduate program is going up exponentially, and I don't think it can continue going that way. But let me just summarize. Okay. We have the program, it is conceived based on educating in multidisciplinary setting. And by doing that, we have brought other engineers to help us teach material science engineering. And there is no MSE department, but it has chair, It has its own staff, it has its own faculty, it has its own money, etc., etc. So we are very, very proud of this, and we think that that's the future for material science and engineering. Okay. With that, I'll stop and answer any questions you have. I know the students need to go to their other classes. Okay. Thank you very much.
So I have a general question. I mean, this is a very innovative concept to take a discipline and kind of spread it across the college. And I wonder if there are some thoughts about other disciplines that might be amenable to this kind of treatment.
Yes, and others are happening, because in at least my own philosophy in engineering education is that we have to have strong core programs. Like, you can't let a person go out as a civil engineer if he or she does not have strong. But what we need to do is make the boundaries fuzzy, diffuse. So we shouldn't just put a block of wall here, say this is where civil engineering ends, this is where the other ones. No, let's have the boundaries fuzzy, spread, diffuse, but have a strong core. And departments are responded, like for example computer engineering now is being offered jointly between CS and EE, rather than saying okay, it's mine or the other. No, we are hiring faculty jointly for computer engineering, that they are 50-50, 60-40 between those two departments. We are getting into educational technologies that will be hiring jointly faculty between CS and, say, School of Education. So we are applying that, but the material science engineering was the first one we did, and because we knew that there is a demand, there are a way of doing it, there are reasons doing it. So, and of course, since I was familiar with the field, I could push it. Okay, thank you. Okay.
Any other questions? Can you shout it out?
How does the state look at this for engineering registration?
How much?
Okay, would one become a professional engineer in mechanical or electrical discipline? How does the student decide which thing?
Yeah, the professional registration really depends on where they end up working. The ones who go to environmental side, they have to become professional engineering. Then they take the exams. They get prepared and so on. But if they end up going, for example, in bioengineering, that professional degree is not, professional certification is not required. Okay. But some of them, yes, they have to take the exam. If they end up working, say, in civil engineering type setting, they have to become licensed professional engineers. But since they have the foundation, they can do that. And since they also have had some specialization courses, they can do it. But if they finish the degree, then all of a sudden they realize that, they have to take that, they may have a difficulty if it is too far away from their initial interest area. You know what I mean? Like, if they are in mechanical engineering, coming through mechanical route, which mostly they are focused in SolidWorks, designs, etc., then all of a sudden end up working, say, in chemical refinery, they are going to have a little bit of difficulty. Yeah.
Any other questions? Oh, what about here?
Okay, yeah. Decades ago, Riverside County had the fastest growing population of any other county in California. Could we attribute that to the founding of your university, or was it for some other reason?
I think both of them are there, but the main reason is that when you look at Los Angeles and Orange County, there's no place for people, things to grow anymore. So it becomes the question of choice and quality of life. We have a lot of people who live in Riverside. They work in Orange County. They work in Los Angeles every day morning. They take, from Riverside to Los Angeles around 60, 70 miles, which one would say that, okay, they can make it in 1 hour. No, sometimes you need 3 hours, okay. But that is one of the reasons that it is growing. It has been growing. And of course, we have influx of migrant workers and others that helps the growth. But Riverside County is huge. I think it is the largest, maybe after LA County as far as square footage. But it reminds me of when I was a student here, places like Walnut Creek, Concord, and so on. You would go there, you would see these open fields and open lands. Okay. Now you go from there to here to there. You don't know when one city ends and when the other one starts. So we are at that level. Like San Diego is now filled, people are moving up. Orange is filled, people are moving this way, and on our side. That's one of the reasons. Okay. But of course, universities, having a research university, UC type university is a major attraction. And we get a lot of industries that start with the faculty's research. The only major difference, say, between us and, say, startup companies in Silicon Valley, when they start in Silicon Valley, there's enough capital there that they end up staying there. In our case, when the company gets certain level, then all of a sudden these people with the money, capital, they come and buy the whole thing, take it elsewhere. So we kind of keep feeding industries that way. But at the same time, some stay and grow. Like Bourns Inc., the company that our department is named after, they started in Riverside and they have now over 4,000 employees all over the world, and Riverside as well. The headquarters in Riverside. Okay. It's a great place. I hope next time you come that way, you stop by. And the only difficulty is that Riverside doesn't have its own airport, but we have Ontario Airport, which is only 15 miles away. That's the one I use. But for international, we have no choice but to use LAX, which, as you can tell, it's not my favorite airport. But there's all the flights that you need. Okay? Thank you. Okay, thank you.